Good morning to dear all. The topic which I am going to discuss today is known as heteroskedasticity. After that, we will continue to the autocorrelation and then we will go to the multi-coordinating problems. Why I'm going to start from heteroskedasticity? There are many reasons of it. It is one of the most confused topic. I have not seen many people who are having clarity on this topic. So I think a detailed research is required on this topic. And after doing a lot of research, so I'm bringing this concept to you, and I hope you will like it. One of the distinct feature of this heteroskedasticity is that it is the longest word in English dictionary, and this word is having 18 alphabets. Okay, so heteroskedasticity. Now you can see that there are two graphs in this slide, and these two graphs represent two different things. The first graph is representing the time series heteroskedasticity. So I call this as a time series heteroskedasticity, and this is cross-sectional heteroskedasticity. So there are two types of heteroskedasticity, one on the time series and one on the cross-section. So what is it? We will discuss in detail. So the topics are the concept, definition, type, source, detection, and remedy. So this lecture will be focuses on these aspects. Now, if you see these three pictures, in these three pictures, we are representing the error terms. Whenever we develop a forecasting model, the difference between the forecasted value and the actual value is known as error term. And this error, if you plot this error, it may be possible that this error is constant with time, the graph number 1. The error increases with the increases value of x, or the error decreases with the increasing value of x. So all the three diagram you can see here, they are representing the error with respect to x. So it is, so whenever we are plotting the error with respect to x, this is cross-sectional error, cross-sectional heteroskedasticity. So in cross-sectional data, which is not a time series data, it is a pure cross-sectional data. The error term may be constant, error term may be increasing, error term may be decreasing. Constant is known as homoskedasticity, and if it is not constant, that is called heteroskedasticity. So the today's session will focus on both cross-sectional heteroskedasticity and time series heteroskedasticity, and many people don't know the difference between the two. So that's why taking both is compulsory. So now you are having some idea that today we are going to talk about the error terms. So it may be constant, it may be increasing, it may be decreasing. So there are different behaviors of the error term. So first of all, I'm going to explain one simple definition of the error term, because that definition is very necessary to understand. Assume that the today price, P0 means today price. Assume that today price will be 100 rupees. Now we are expecting that P1 hat means expecting. So we are expecting this price to be 102. If there is no news in the market, if there is no movement in the market, so we are expecting the price to go up by 2 rupees. This we are expecting. Now the actual price may be equal to forecasted price, but it is very rare. Actual price never equal to forecasted price, it is away from that. Now assume that this price, actual price will be 110. Now what is the error term in this case? The error will be equal to, error is always equal to actual price minus forecasted price. It means 110 minus 102. Now it is plus 8. So this error, which is of plus 8, has two properties. This is known as sign effect of error, and this is the size effect of error. So sign is representing the response of the investors. So because the error is positive, it means the suddenly next day investors are highly positive toward the stock and they start buying heavily. Because of the heavy buying, the stock price moved from 100 to 110. So this 8 is this plus sign is representing you the sentiment. So if I ask you a simple thing, what is the sentiment of the investors or market participants toward the stock on next day? So you are saying that the sentiment of the investors are highly positive because that's why they are buying the stock. So this is called sign effect of the error term. Now the question is that how much they are positive. So we are clear that the investors are positive. That's why they are buying the stock. The question is that how much they are positive. So that is called size effect. So plus 8. Plus 8 means the expected positive sentiment is 8 rupees greater than the expected price. So this is called size of the sentiment. So error term in any day is consisting of two aspects. One is the sign effect and the size effect. Now the question is, can we say the sign effect and the size effect is same all the days? Answer is no, because it is even for a human being, it is not possible to have the same mood all the days. Someday you are very happy, someday you are having very sad. If I want to forecast you on a next day, so your mood if found to be positive, that is called positive sign effect. And we can also calculate that how much it is positive, size effect. You know that happy, very happy, extremely happy, size effect. Sad, very sad, extremely sad. So this error term, which is the difference between the actual behavior minus expected behavior, is represented by sign and size. And heteroskedasticity will address why this size effect is changing every day. Like for example, if we plot this error term, the error term should comes like this, but it is never like this, because this is a should be behavior. Should be behavior means the size effect should be same with all the days. This is called homo. Homo spread. Spread means skedasticity. Homoskedasticity. Homoskedasticity means the error variances should be same. It means what we are saying that the size effect of the error term should be same on all the days. Now, by common sense, if we think it is not possible, because human being as a human being, we are not, our behavior is not same on all the days. So how the stock market is possible, or commodity, or any other market? So in actually, the size is sometimes the very low, sometimes it is very high, sometimes it is very low, sometimes it is very high. And we can say these periods are called stable periods, and these periods are known as volatile periods. And because of this actual concept, this is a concept which is actually there in the market. The heteroscedasticity concept is very important. So when the market mood is changing with time, this is known as in mathematics we call it error variances are not equal. The error variances are not equal. This concept is known as heteroskedasticity. So I'm just putting a short form of it. This is the concept of heteroskedasticity. It means error variances are not same on all the days. With cross-sectional heteroskedasticity, we are representing with respect to x, with respect to independent variables. When independent variable changes, the variance also changes, maybe increasing, maybe decreasing. So that's why the heteroscedasticity is one of the important concepts, and many reviewers ask you to deal with it. So how to technically deal with it, that we will cover today. Now, coming back to this slide, in whiteboard, I explained you how we deal with the error term. What is the meaning of the error term? Error term is having two components, size component and sign component. Now, if you see these graph, as x increases, so here income is the x-axis. So you can see the variation in the error term. This line is the regression line, and this is the variation in the distribution of the error terms. And you can see it is a very ideal condition that distribution of the error terms are equal. This concept is called homoskedasticity. However, in the second graph, you can see the error variances increases with x. This is called heteroskedasticity. And because we are plotting the error term with respect to x, this is called cross-sectional heteroscedasticity. So cross-sectional heteroscedasticity is representing with respect to the independent variables, and the time series heteroscedasticity is representing with respect to time. So from this graph, these two graphs, now I'm asking you a very simple question. Suppose I keep this error term as a dependent variable, and keeping X as an independent variable. Do you feel there is any relationship between them? Right. So think on this line. So I'm saying, do you think the error term, if I take this regression model, x1 plus beta 2 x2, so I am plotting this error term with respect to x. The simple question is that, do you feel there any relationship between the error term and the x values? This is the basic root of all the tests. All the heteroscedasticity tests are based on this concept. If you see this graph carefully, this graph is telling you that x increases, the error variance also increases. Or in other case, if x increases, the error variance decreases. So all the Breuschwagan test, White test, Gls test, right? They are doing all heteroskedastic tests by taking the relationship between the error variances and the x-axis or x variables, independent variables. So now, one conclusion that we are drawing from here, that the heteroskedasticity means the unequal error variances somehow they depends upon the independent variables. And in time series heteroskedasticity, it depends upon the time. So these two you have to keep in your mind, because in coming slide we are going to discuss the advanced test. Okay, so by definition, an important assumption of linear regression model is that disturbances are homoskedastic. The first graph, they have all equal variance like this, but it is not possible in most of the cases. So the violation of this assumption is known as heteroskedasticity, and we are dividing into two categories: cross section and time series. Especially in time series, because in this case you can see the x-axis we are having the time. Just see this two circles, and we are saying that the variation in the behavior, greater variation between consecutive values, a smaller variation between consecutive values. So it may be possible that as time proceed, the high variation is found in the price, and it is because of the increase in price. When price is very low, like 100 rupees, the variation may be 2 rupees, 3 rupees. When it is around 1000, the variation may be 10 rupees, 20 rupees. So sometimes with increase in the price, the variation may be low, high. So this is one of the basic reason of the heteroskedasticity in the price series. The other reason is the behavior of the market. So that we'll also understand. So the heteroskedastic concept is very common in time series as well as in cross-sectional data. So both type of heteroskedasticity we are going to discuss. Now the basic question is that why it comes? Why heteroskedasticity comes in the behavior? The first is the literature says that one of the reason of heteroskedasticity is error learning model. According to this model, people learn from their errors, mistakes, and slowly the error reduces with time. So sometimes the error reduces with time, especially if you're talking about the learning. Like for example, hours of typing practice. So if somebody doing typing practice in one, initially it will take more time, and slowly it will take less time. Like for example, if we talk about the publication, the first publication for first scholar or for a new scholar, the first publication may come in 3 years. But after some time, in 1 year, there are 3 publications. So number of publication increases with time. This is called error learning model. So with time, you will do less mistakes, so error terms will be less. So this is one simple reason. Outliers. Outliers means extreme behavior. In stock market, you can see a lot of flash crash. Flash crash. Flash crash means suddenly the market crashes. Like last week, we have seen a flash crash. Suddenly the market opens and crashes. Even on Thursday, I have seen a huge flash crash. So these crashes are known as flash crashes. Dekhte hi dekhte market gir gaya. So like flash crash. Because of these flash crashes, and they're not very common. It comes hardly in once in 2 years. Flash crashes are not very common. It comes very rare. So they are outliers. And because of these outliers, the market becomes volatile suddenly. So you can see the market is volatile during short period of time. And the research say that the average duration of the flash crashes, or flash crashes means because some sudden news, the market becomes volatile. The average volatility period is 66 days. So because we are researchers, so we know that whenever some problem comes in the market absorbs this problem in hardly 66 days. Like for example, now we are facing the problem of interest rate increase, and you can see after 2 months, the market will absorb this news. And once the market will absorb this news, it will come again, coming back. And but it may be possible that some other news will come. If no other bad news will come, then it will absorb. Like in Corona case, the market crashes in the month of March, April. After May, it will come back. It started coming back. So this is the behavior of volatility in the market, and all depends upon heteroscedasticity. Then miss is specification. Sometimes you are not adding important variables in the regression model, and because of these important variable in the regression model, the error terms becomes volatile. So this is also a reason. And the last reason, which is the most important reason in the time series, is clustering, volatility clustering. What is the meaning of volatility clustering? You can remember your behavior. Sometimes if you are very happy, the next day, the chances are very high that you are happy again. So happiness will carry forward. And if you are very, very sad, the chances are very high that on next day your behavior is also sad. So the mood always comes in cluster. Mood, behavior always comes in cluster. So you can feel this kind of behavior in yourself also. The happiness stay for some time, or sadness also stays for some time. If you are happy for some days. If you are sad for some days. So this is called clustering. So let me, if I plot this graph, if market is volatile, it is volatile for some days. If market is happy, it is happy for some days. Then it becomes volatile. So you can see that the volatility comes in cluster. This is the cluster. And this clustering is 100% there in the market. It's very common. It's there in always stock prices, commodity prices, exchange rate, everywhere. Even if you plot your behavior at the time, you can see this behavior also. Some days you are very happy. This is not happiness, this is sad, volatile behavior. This is happy behavior, and this is volatile behavior. So because of this volatility clustering, we can check the heteroskedasticity in time series with a different equation, with a different model. So when I say volatility clustering, in this case, the error term is not depends upon X independent variables. The error term depends upon the previous value. Like if yesterday you were sad, today the chances are very high you are sad also. And the sadness is coming from yesterday. So the error term of any day depends upon the previous error term. So this is also known as auto-regressive heteroskedasticity. If you think on this word, auto-regressive heteroskedasticity, it means the error term of any day depends upon the error term on previous day. This is auto-regressive. So Arch test is also a test for volatility clustering. So we will also do volatility clustering test today. So these are the basic reasons which I found very common reasons of heteroskedasticity. Okay. Now the question is that what happens if your error terms are heteroskedastic? What is the impact of heteroskedasticity on the regression model? Now this line is also very important. Everybody should know it. Basically, when heteroskedasticity is there in the error terms, it will not affect the coefficient term. It will affect only the standard error of the coefficient. Whenever you apply the regression model, you know that the beta will come, and with the beta, a standard error of the beta is also coming. So the theory say that the regression coefficient are still linear, consistent, and unbiased. Linear, consistent, and unbiased means even if you increase the sample size, they will not change. So consistency in the regression coefficient will be there. Regression coefficient means slope coefficient. So they are still linear, consistent, and unbiased. But what is lost? The loss is that the error terms are very high now. In fact, the variance of the error term do not influence the unbiased property. However, they are no longer efficient or best. They are no longer efficient or best means the error term are now having high variations. Because of that, the standard error of the beta coefficient are also increases. So the best property of the slope coefficient are missing now. The forecasting errors are now high. So this is a problem. And how to solve that problem? We have to see. Because if reviewer asks you that in case of the presence of heteroskedasticity, the standard error of the slope coefficient increases, how you deal with it? A very basic question. So you must have the answer of these type of questions, that because heteroskedasticity is a very common problem, it is there in the model. So how we deal with the standard errors of the slope coefficient? So now in the coming slide we are giving the answer of it. Yeah. So this behavior is same in cross-sectional as well as time series. This property is same for both cross-section and time series. Now the question is that once we understand what is the heteroskedasticity, the question is that how to check it. How to check it? Now there are two type of methods of testing the heteroskedasticity. One is the cross-sectional testing, and second is the time series testing. The three equations which I write here, it is for cross-sectional, time series, and the multivariate linear model panel data. In all the cases, you can see that x-axis is one of the reason of this heteroskedasticity. So this is the one method. So we are okay. So these are the regression models, and after that we will regress the error terms with respect to x and with respect to its previous value, because these are the models, regression models. Testing of the heteroskedasticity, let me write here. Testing of the heteroskedasticity depends upon two things. So one is u is representing, suppose u is representing the error term is a function of x1, x2, and so on. So we are assuming that the error terms is related to the independent variables. This is the cross-sectional testing of the heteroskedasticity. And if I say ut and ui, I means the cross-section and t means the time series. And we assume that ut is a function of u t minus 1, u t minus 2, and so on. So these are the two methods of testing the heteroskedasticity. And I'm in this slide, I'm mentioning different tests. And all these heteroskedasticity tests are representing only the cross-sectional part. And one thing is common in all the equations. And if I compare all these tests, two tests are very, very common. The first is Breuschwagan test. It's very common. White test, very common. All other tests are not very popular in the literature. Now, just see the equations. The Breuschwagan test is representing in this equation, square of the error terms is a dependent variable, and x1, x2, x3 are the independent variables. So all the independent variables are independent variables. Only thing is that we are replacing y with the square of the error terms. So this is simple Breuschwagan LM test. Glaser, Harvey, Godfrey, all these tests only replace the dependent variable. Glaser consider modulus of the error term as a dependent variable. Harvey, Godfrey represent the log of the, so this take the log, natural log, ln means natural log of the square of the error term. In the left hand side is the right hand side in this equation are same in first three. Park LM is taking the log of all independent variables and the dependent variables. Godfeld is not very popular test, only applicable for the bivariate regression model. But if you see the white test, now there is one difference. In white test, the dependent variable is same as in Breuschwagan test. The only difference is that it is taking the product of xi, x1 into x2. So in white test, not only independent variables are considered, but their square and the interaction effect is also considered. So if you compare all these tests, so you can say the white test is the best of the test. Why? Because we are not taking only independent variable, we are considering their square, we are considering their product, interaction effect of the independent variables. So that's why white test is one of the most popular tests used for examining the heteroskedasticity. So white test is number one, Breuschwagan is number two. So as per my knowledge, these two tests are very, very popular for testing the cross-sectional heteroskedasticity. I'm not talking about the time series. So I'm talking about the cross-sectional heteroskedasticity. In time series, we are using the Rcm test. So Rcm test is used for testing the time series heteroskedasticity, and white test, Breuschwagan test is testing the cross-sectional heteroskedasticity. So these two type of tests we are going to use. Okay. So the null hypothesis of these tests is that the slope coefficient of all the equations are 0, it means the independent variables are not affecting the error terms. If independent variables are not affecting the error terms, it means there is no heteroscedasticity. It means the error terms are homoskedastic. But violation of this or rejection of this hypothesis means the error terms are heteroskedastic. So this is the basic test that we are going to do. Now, in detail I write this test. Otherwise, they are just same. Now I'm going to show you with the EVUs that how we can check the heteroscedasticity in the series. So two examples I will do, one on the cross section and one on the time series. The purpose of doing these two tests is how to examine the heteroscedasticity in the series. So now I'm going to open the EVUs and we'll use two type of data set. So first of all, I'm going to show you the heteroskedastic data. I will put this data in the drive. So after this session, you will take it. So in this data set, the y is my dependent variable. And there are four independent variables, x1, x2, x3, x4. So just select y, x1, x2, x3, x4. Now open as an equation. So we are going to run this equation. Okay. And you can see that the x1 is not found to be significant, but all the three independent variables are significant. And if I'm talking about these standard error, what happens if your model is suffering from heteroskedasticity problem? The error terms are coming higher side. Okay, now how to check whether the error term of this model is heteroskedastic or not? So go to the view. So you can see this view option and residual diagnostics. In residual diagnostics, we are having the heteroskedasticity test. If you click on heteroskedasticity set, all the tests you can see here: Harvey, Glaser, Arch, White. So all the tests are there. Now, if you click on Breuschwagan test, the dependent variable is residual square and regressors are these. If you click on Harvey, the dependent variable is log of the residual square and these are the independent variables. If you click on Glaser, dependent variable is absolute of value of the residual and there is no change in the independent variable. Arch, this is for time series. White, dependent variable is residue square and the independent variables are the squared values of independent variable and the cross product of original regressors. Right. So we are having different type of tests. Now I'm going to apply first Breuschwagan test. Okay. And we have three measures: F statistic, observed value, number of observations multiplied by the R square, and P value in both the cases are less than 0.05. So we assume that the errors are heteroskedastic. So problem is there. In simple language, the problem is there. Okay. So similarly, if I go to the next test, let's say white test, because I will in the session I will use only white and Breuschwagan test. All other tests are normally give you the same result. Now, if I apply the white test, you can see the equation is now very complicated. X1 is square, x1 into x2, x1 into x3, x1 into x4. So degree of problem is there in the white test. White test is only applicable when you have large number of data set. Otherwise, white test is not applicable on the small data. So this is a problem in a white test, that it is not applicable on the small sample size. It is only applicable on the large sample size because the number of independent variables are very high. But the conclusion is same here. The error terms is heteroskedastic. Okay, so two tests I have shown you, and I hope you understand the meaning of BP test and white test. Now I'm showing you the another test called time series heteroskedastic test. Okay, so let me take another data set. The data set we already have. Yeah. Now in this data set, suppose gold is my dependent variable, and bonds, gold, bond, crude, and Nifty and USD INR. So these are my independent variables, and I open as a equation. And you know that all these series are the non-stationary. So I am taking the D log because regression should not be applicable on the original values because of the time series unit root problem. So I am taking in all. D log means log difference. Okay, and if I run it, so still they are significant. So gold is affected by all these series, and Darwin-Watson test is representing that there is no auto-correlation problem. And now I'm going to check the heteroscedasticity. But which heteroscedasticity? Now I'm going to check the Rcm test. So Rcm test, I'm going to examine whether the error terms according to the time is heteroskedastic or not. And click OK. And in time series, it is very common. Okay, let's do one more thing, one more time. So one thing which I want to show you here, the dependent variable is still residual square. In all other tests, dependent variable is also a residual square, error square. But as an independent variable, we are taking the lagged squared residuals and a constant. So if I take 5, it means I am taking 5 independent error terms in this. Like you can check. So in this equation, the dependent variable is residue square, and independent variable is previous day, 2 days back, 3 days back, 4 days back, 5 days back. So error terms on the previous days become the independent variable, and this concept is called auto-regressive heteroskedasticity. So in time series, we to understand the concept of volatility clustering, we use this test. So the null hypothesis is rejected here also. And if you want to check the residual graph, so you can see the clustering. So for example, this is a stable period, this is a volatile period. So in some volatile periods, some stable periods, this is a volatile plus period. So volatility comes in the clustering. So that's why error term of any day depends upon the error term of previous day, and lag 2, lag 3, lag 4, like that. So in this way, we are examining the heteroskedasticity in a time series data set. Okay, so I have shown you the testing of heteroskedasticity in both type of data set. So we have two data set here. One is the heteroskedasticity cross-sectional data, and one is the time series data set. So in this way, we can check whether the heteroskedasticity is there in the error terms or not. So I hope you understand how to detect the heteroskedasticity. Okay, so come back to the slide. Okay, now the question is that how to solve this problem. The most important concept is how to solve this problem. So there are 3 methods of solving the problem. One is that changing the forms of the dependent or independent variable by changing the functional forms. Divided. So these are the different methods. I will show you different method. Divided by dependent variable, log-lin model, log-log model, divided by the error terms, etc. So there are 4 functional forms which we can apply to remove the heteroskedasticity. And second method is that we can apply Gls method. Then there are the third option is that you can find out the best standard errors of the model. So there are 3 methods of removing the heteroskedasticity as I found in the literature. So I'm showing you one by one. The first case I'm showing you is how to check the functional forms. Okay, so let me show you the first method, how we can check the different functional forms of removal of the heteroskedasticity. Let me open the data number 1, and 4 forms I will show you that are available in the literature to remove the heteroskedasticity. So first of all, let's run the equation. You have to select all these in sequence. The first variable I selected is y, and all others are independent variable. So the sequence which you select, you can see the same sequence here, and okay. Now in this case, we examine the heteroskedasticity. Let's check from the y test or Breuschwagan test, and we know that they are heteroskedastic. So if you go to the estimate, you will come back to the equation again. Now I am saving one thing. If you go to the proc, click on the proc forecast. So I am saving the forecasted values of y. The forecasted value of y is saved in the name of yf. Okay, and these are the forecasted values. So forecasted values of y, you can see this is the forecasted value of y. Okay, now this is our equation. I am dividing each term by y forecasted. So my dependent variable and independent variable are divided by y forecasted, yf divided by yf divided by yf. So now I am running the new regression model where every variable is divided by the forecasted value of y. So this is the result, and I want to check whether still heteroscedasticity there in the model or not. So view residual heteroskedastic Breuschwagan test. Now you can see the heteroskedasticity is gone. The heteroskedastic problem is gone. So this is the first form which is used in some cases to remove the problem of heteroskedasticity. Now I'm second. Okay. Now second is log lin model. Log model, lin model. So how to check that? This is the form number 2. So I'm taking the log of only simple log of y and nothing else. So now I'm just taking this model is called log linear model. Log linear model means we are taking the log of the dependent variable and not taking the log of independent variable. So this model is called log linear form. And the R square is 93. And let me check whether this is still heteroscedastic or not. So I'm testing the heteroscedastic test, Breuschwagan test, and this form is not very helpful. So but in some cases it may help you, but in our data set it is not helping us. So that's why I'm moving one step ahead, that is log format. So I'm taking the log of all independent variables also. This is called log format. So this is also adopted by most of the researchers to remove the heteroscedasticity. Now if I take the log of dependent variable, log of independent variables and click OK and find out the heteroscedasticity, and you can see the heteroscedasticity is gone. So one of the reasons in literature that why people take the log of the different dependent and independent variables is also to remove the heteroskedasticity problem. So when you take the log of dependent variable and independent variable, the chances are very high the heteroskedasticity will go. So this is one of the popular method of using removing the heteroskedasticity. So 3 forms I have shown you. Now the last form which I am showing you, just see. Okay, so I'm coming back to the, okay, let me delete it. So the last form which I'm showing you is also helpful. So again, I'm taking the dependent and independent variables, opening as an equation, running the model. Now I'm saving the error terms of this equation. So you go to the proc, you go to the residual series, and this error term, this is the error term series. So I'm saving in the name of error. And okay. Now you can see that some of the error terms are positive, some of the error terms are negative. So we are having a problem with positive and negative. So I'm going to square it and then take the square root. Let me okay. So I'm going to quick generate series. So I'm taking a series in the name of res residual equal to the error series is the saved series. I'm taking the square of that and then taking the root of that. The square root of that. So first of all, I'm going to square it, then taking the under root. So this is my residual term. It is simply the removing the sign. So now all the terms are positive. So the equation which I'm going to run now is, let me write here, y divided by the error is equal to alpha plus beta 1, the x1 divided by the error plus beta 2 x2 divided by the error, like that. This is similar to the GLS model. You can take the square of that or you can take the square, that is your choice. Both are okay. So now I'm running the modified form. My dependent. So I have the equation here. If you go to the estimate, you will come back to the equations. And now I'm just dividing it by residual. So I'm dividing the each term by residual, and this is the equation now. And if you check the heteroskedasticity of it, and you can see that now the error terms are homoskedastic. So this is similar to the called generalized least square. Generalized least square. So this is also one of the popular method of removing the heteroskedasticity. So after that, because we have completed the functional forms. So as I told you that there are different functional forms which are used to remove the heteroskedasticity. So first of all, I divided by the forecasted y. Take the log-lin model. Log model. Log-lin means taking the log of dependent, leave independent variable as it is. Taking the log of dependent as well as independent, divided by the error term. So these are the different formats which are available to remove the heteroskedasticity in the literature. The second is GLS. Now this GLS is slightly different from the GLS model that we take. Let me show you that. What is GLS? The method which I just showed you is this, that I take the square root of the error variances and divide the dependent variable, independent variable by this and run the new modified form. So this procedure of transforming the original variables in such a way that the transformed variables satisfy the assumptions of the classical model and then applying OLS to them is called method of GLS. So sometimes GLS is used to remove the heteroskedasticity problem. It is recommended by many researchers that if your regression model is suffering from heteroskedasticity problem, you can go for GLS. This is also one method available. Now, the slightly different method from GLS is WLS, weighted least square. So we have another format of GLS. So this is just another equation I represented by GLS. So first of all, I run the original equation. Then I save the heteroskedastic variances, means error terms, and then take the square root of the variance, divide all variables by the error term, and run this model. This I already showed you. The another case is called weighted least square. So this weighted least square assume that you are not aware about the error variances. So you can take some independent variable to apply WLS. In GLS, we are using the weight 1 upon sigma I. But in this method, so I explain this method here. Sometimes we have difficulty to estimate equations because of this problem. It is unknown. So there is another method. Need to have prior knowledge about the, okay. So we are taking the Zi, right, which is a known variable. Non-variable means it is one of the independent variable. So we can also use the independent variables rather than the error terms to apply WLS. So in simple language, what is the difference between GLS and WLS? In GLS, we are dividing all the variables, whether dependent or independent, by the error term. In weighted least square, we are dividing the dependent and independent by any of the independent variable, so that we can give the weight. And what is the reason of WLS? The weighted average least square assume that this is only because of independent variable, the heteroskedasticity is coming. And because of, so if we find out the most notorious independent variable, we can take that independent variable in the denominator and rerun the model again. So this is the concept of weighted least square. So we can also apply the weighted least square in EVUs. Let me show you the procedure. So these two methods are popular method of removing the heteroskedasticity. So I'm going to show you how to apply WLS in the EVUs. GLS, I already show you how we can apply the GLS model, how to save the residual and divide each variable with the residual and apply the modified format. In another case, I'm taking the Y and let's take the independent variables. So open as an equation. And if you go to the option, so you can see there are many options available here. I think this method. So ARM options. Yeah, actually in EVUs 10, this option is here. And so I'm going to apply weighted least square. So weight, which is the weight you have to apply? First of all, inverse standard deviation. You have to select this. Weight series, let me take x1 power minus 0.5. So I'm taking the weight of x1, let's say. So this is you're now you are getting the weighted least square model where weight is assigned by the x1. And if I go to examining the heteroskedasticity, so it's still there. So it means x1 is not contributing to the heteroskedasticity. Similarly, I will go for another model x2 power minus means I am going to take it 1 upon, because weight is always 1 upon z. So minus means 1 upon 0.5 square root of that. So I'm taking the square root of that. Okay. And similarly, you can check with all independent variables and you can find out that which variable is creating problem in heteroskedasticity. So still this is also not a problem. X2 is also not contributing to the heteroskedasticity. Let me go again back. Estimate option weight. Now I'm taking the x3 power minus 0.5. Okay, and let's take heteroskedasticity. Okay, so still x3 is not found to be significant. So the meaning which we are getting here, heteroskedasticity is not coming from one single variable. And let me check the last option, that is x4 power minus 0.5. And okay, let me check. So in this case, I think the one variable is not contributing to the heteroskedasticity. So this WLS is not working here. So WLS is mostly used when one or two variables are main variables causing the heteroskedastic problem in cross-sectional heteroskedastic data. So the way we run WLS is now clear. And so in this, for this data set, the two forms are found to be highly beneficial. One is the log-log format. So when I apply the log-log format, we have seen that the heteroskedasticity was gone. And second, the GLS method, when you divide each term by the square root of the error variances, then also the heteroskedastic problem was gone. So this is the conclusion that we can draw from the testing of the heteroskedasticity. Okay. Now I hope you understand what is the GLS and WLS after this example. Yeah. So we have completed the first testing. We have completed the second testing, how to examine the GLS. But these two methods are mostly applicable in the cross-sectional heteroskedasticity. The third test is applicable in both time series as well as cross-sectional also. White, robust, standard error. Now we are having two methods. These two methods are known as Huber-White consistent standard errors and Newey-West consistent standard errors. So two methods now I'm going to show you. The first one is Huber-White standard error, Huber-White, and the second is the Newey-West standard error. So these are two most popular tests available in EViews. Now let me explain the concept of these two. As we know that the heteroskedasticity can be removed by different functional forms. But suppose if you don't want to change the format, if you don't want to take log, because in time series we already take the log, so we can't take the log of the log. We cannot change the forms, right? Especially in time series, because it is already d log. Then what to do? The answer is that you can apply Huber-White method or Newey-West method. These two methods will not change the slope coefficient. They will only give you the standard error, which is corrected from the heteroskedasticity. So as I told you that in the presence of heteroskedasticity, there is no change in the slope coefficients, only the standard error will increase. And because of the high standard errors, the t statistics are sometimes coming wrong. The hypothesis testing is misleading. So that's why, to remove that misleading problem of the hypothesis testing, if we correct the standard error, we are getting the true test of hypothesis. So they will only change the standard errors of the slope coefficients. They will not affect the beta coefficient. They will only affect the standard errors. Now the new standard errors are the true standard errors, not the inflated standard errors. And if you have true standard errors, you have true picture of hypothesis testing. So one method is called Huber-White. Huber-White is applicable only when your model is suffering from only heteroskedasticity. Huber-White method is applicable only when your model is suffering from heteroskedastic problem. The more modified value format is Newey-West standard error. If your method, if your regression model is not only suffering from the heteroscedasticity, but also suffering from the Durbin-Watson problem, autocorrelation problem. Durbin-Watson is known as autocorrelation problem. So in case of both problem, you can apply Newey-West standard error method, right? So this method is highly consistent. So now I'm going to show you that how these two methods will work and how to interpret the meaning of these two methods. So after that, the heteroscedasticity problem will go. And let me show you the procedure of both. Okay, let me show you in this data set because procedure is exactly same. Now I am going to apply the regression one, and I know that this model is suffering from heteroskedasticity problem. Okay, so let me run the equation. This is the simple equation we are running, and we know that this is the basic equation, and this equation is suffering from heteroskedasticity problem. So I just freeze it. So when you click on freeze, the result will come. Okay, then go to the estimate. I also freeze this result. So these two results are original results. Now I keep these two results for comparison. I'm just going to the estimate, going to the option, and you can see that the option that coefficient covariance matrix, I have two options, white and hack. White means Huber-White, and hack means Newey-West. HSE means heteroscedasticity autocorrelation consistent model. So white, okay. Now you are getting this result. So let's freeze it. Okay. So what I'm going to show you is that, yeah. So if you can see the error terms are different. The error terms are different. The error terms in original are different. Error terms in new are different. So, however, in this error term, slightly high error terms are coming, but these error terms are true error terms, standard errors, and coefficient is already same, minus 0.012, minus 1.855. So there is no difference in the beta coefficient, slope coefficient, but you are getting the better error terms, which will give you better results of probability testing. So because of this standard error, the t-tests are different, and because of the different t-tests, your probability is different. This probability and this probability are now different. But in the second method is heteroskedastic consistent standard errors, which are giving you better picture, and the probability values are now better. Otherwise, all other things are same. Even R square is also same. So everything is same. The Durbin-Watson is 0.99. It is also 0.99. So everything is same. FS statistic is 143. It is also 143. But only thing is that you can write in the paper that we applied Huber-White consistent standard errors, because now your hypothesis testing is more accurate as compared to previous model. So this is called White consistent. And another next method which I'm going to show you is Newey-Hack method. So I'm just deleting it. This I just put for comparison. So the new results are giving you better standard errors for better hypothesis testing. And let's go back. Whenever you want to go back, just go to estimate and go to the options. Now white test is only removing the heteroskedastic problem, and if you apply on hack, heteroskedastic autocorrelation problem is gone by this. So again, even in this, beta coefficient will be same, only the standard error will be different. So all these standard errors are now totally different from others, and your hypothesis testing is much better. And this method solve the problem of autocorrelation and heteroskedastic, and giving you the true standard error so that your probability will be same. Otherwise, there is no difference between any of the result. Even if you check, heteroscedasticity will be there. It is still there, but only difference you are getting is the new standard errors, which will improve the probability of hypothesis testing. So because most of the scholars, I found that they don't understand what is the meaning of this Huber-White and the hack. The only difference is that they are giving you different error terms, different standard error of the slope coefficient, which increases the accuracy of hypothesis testing. This is the only reason that we are using the Huber, White, and Heck. Okay, so after this, I'm just going to show you one more thing. This is because this is regarding the cross-section data. Now let me go for the time series data. In time series data set, let me open as equation. This is my equation. If I run this equation without taking the D log, the Darwin-Watson is a problem here. And not only Darwin-Watson, the heteroscedasticity is also a problem. But we are not going to apply any other test. We are going to apply Rcm test, and it is a problem. So both problems are there. Let me try one or two forms to check whether they will impact my model or not. Let me take first D log. Okay. After this, when we go for D log, this Darwin-Watson problem is solved. Okay, but this is of Rcm test. Now you can see that in previous equation, Darwin-Watson is very low. Now it is solved. And if you check the standard errors, so they are coming different. And if I apply, okay, let me freeze it. This is for comparison. Okay, so this is the freezed results. And again, I'm going to where is the equation? Estimate. Yeah, so I freeze the results. I'm going to apply the White test, and the error terms must be different. So you can see that the standard errors are different from this. So you can say that now we are having better picture of probability testing. In this case, 0.07 is similar, close to very 0.05, but here it is totally insignificant. So we can conclude that the Nifty is not having any impact on gold price. But here the conclusion is wrong, that if it is suppose by chance it is coming less than 0.05, then you assume that the Nifty is also having an impact on the gold price. So, but the problem, this problem is coming from the presence of heteroskedasticity. So whenever you run any time series model, for a better hypothesis testing, advise you to apply Huber, White also, so that you can say we calculated the heteroskedastic consistent standard errors so that our hypothesis testing is more accurate. Similarly, you can also apply the Heck Newey test, and the difference is, you can see clearly now it is 28. Earlier it was 0.25, it is now it is 0.28. So Heck method is giving you better picture of standard error so that your hypothesis testing is more accurate as compared to any other model. So these two things which I want to show you. And another thing which you must know, that after running this model, this is a Heck consistent standard error method. If you go for residual graph, this residual graph is showing you the clear picture of volatility clustering. This volatility clustering is now has to modeled again. So we can apply the equation on this volatility clustered error terms by Garch model. So Garch model is starting from this point. If you go to residual diagnostics, heteroscedasticity, Rcm test, showing heteroscedastic, clear heteroscedasticity. So when this volatility clustering is found to be significant, this is required to be modeled by using the Garch method. So Garch method starts from this point. So GARCH means generalized auto-regressive heteroskedasticity. So Garch model is the genesis of the auto-regressive heteroskedasticity problem. So this is the point which you should know. Okay, now I'm showing you one more thing. That is called two other problems we have in the regression model. One is the multicollinearity, and the second is the Darwin-Watson problem, autocorrelation problem. So if you run any regression model, so let me check, do we have the equation? But this is, I think, no, it is a freezed result. So if I run this model once again, the autocorrelation problem is represented by the Darwin-Watson, and in time series, Darwin-Watson problem is very common. Darwin-Watson is always found to be less than 1 if you are using non-stationary time series. So the only and only method to remove this Darwin-Watson problem is to take d-log. So Darwin-Watson problem is can be solved by taking the d-log. After taking the d-log, the problem is already solved. So there is not much to talk about the Darwin-Watson test. So I am taking the d-log of all the variables. And after that, you can see the Darwin-Watson problem is gone. So Darwin-Watson problem is not a big problem in time series. Just by making the series stationary, you will never have the problem of Darwin-Watson. Another thing is that if you go to view coefficient diagnostics, and you can see the option called variance inflation factor. The variance inflation factor is used to examine the presence of multicollinearity. Variance inflation factor should be less than 3, and if they are less than 6, then it is already normal, but beyond 6 it's a problem. So if I click on variance inflation factor, so most of the variance inflation factor you can see is near less than 3. So less than 3 is not a problem. Variance inflation factor less than 3 is not a problem. So these two things you can check whether your model is suffering from the multicollinearity problem or Darwin-Watson problem just by two simple tests you can apply. One thing which I want to again explain, that suppose you are having the y values, let's say y1, then you are having y2, y3, y4. These are the values of y. Similarly, you are having the values of x1, x2, and similarly you are having the values of error term. So these are the error terms. Suppose this is et and previous error term is et minus 1. So what we are doing, et minus 2, et minus 3, we are making another series, et minus 1, et minus 2, et minus 3. So now you can see that you are having two series. This is called et series and this is called et minus 1 series. Autocorrelation is simply the correlation between the two series. What is autocorrelation? Autocorrelation is simply the correlation between these two series, and that's why the autocorrelation is also known as serial correlation. Serial correlation. And the serial correlation is problem. This is a problem because error terms should not be correlated. And if they are highly correlated, it only means that your model is having non-stationary series. This is the only problem of time series because of non-stationary series. So you just do one thing to remove the serial correlation problem or autocorrelation problem. You just take the log difference values of the dependent and dependent variables, or especially those variables which are non-stationary, and the problem will go. You can see that. So this is not an issue. And the second problem which we are talking about, the multicollinearity problem. In multicollinearity problem, which is not a problem of time series, it is more of a problem of the cross-sectional data. But if you want to check the multicollinearity problem, you can just go to the view, coefficient diagnostics, and variance inflation factor, and show them the all the centered VIF is less than 3. So multicollinearity problem is not there. It's a huge problem in cross-sectional data. And to solve this problem, we go for factor analysis or principal component analysis. But in time series, this problem is a rare problem because after transformation, the correlation, most of the correlation is gone. So that's why multicollinearity problem is not a problem, much problem in the time series data set. And Darwin-Watson can be solved only by the taking the d-log. So that's why I'm not taking these two problems in much detail. So today we have done the most important concept of time series, that is called heteroskedasticity, and two other problems we also just see. So I hope that's it for today's session, and I hope you are now having clarity on the three aspects. So I'm just going to unmute you all. So give me a minute.